Hi, everyone. Thanks for tuning in. I'm Meghna, a machine learning engineer at SigOpt. And today we're going to talk about EfficientBERT, trading off model size and performance with scalable hyperparameter optimization. So before we jump into the use case, I'm going to quickly go over what we do at SigOpt and the product features we'll use for this use case. At SigOpt, our mission is to amplify and accelerate your model development and to help you gain insights throughout your experimentation process. We understand that modeling is messy and difficult to standardize, training can be a crapshoot and difficult to debug, and that tuning is expensive and difficult to scale. So we've built solutions to help with these problems, including intelligent experiment management to organize and collaborate with your team throughout your modeling process, providing insights into your training runs, and efficient, intelligent, and scalable hyperparameter optimization. We know you're iterating on tooling along with iterating on your model development. And we've made sure we're easy to use and stack agnostic. For this talk, we'll focus on hyperparameter optimization at scale, and specifically SigOpt's HPO feature. So here's how our general optimization loop works. We set up a parameter space. SigOpt samples the space and provides parameter values. We'll run a model training given these suggestions, and return the model's performance or other metric back to SigOpt. So the optimization process proceeds in this loop-like fashion, where over time, we should see our model performing better and better. Great. Now that we're more familiar with the tools we'll be using along with Ray, let's talk about compressing BERT. So BERT is great and is a very pivotal architecture. It is generalizable and transferable, which means that the model performs strongly across a variety of NLP tasks with very minimal changes required in its architecture. This really enables us to use transfer learning and leverage large pre-trained models to solve specific and niche problems, which is really convenient. But it is very large and difficult to put into production systems and other memory-constrained applications. So many teams are trying to solve this problem by compressing BERT, including Hugging Face, Raza, and Utterworks. We'll be focused on expanding Hugging Face's work on Distilling BERT and specifically ask the two following questions. One, can we understand the trade-offs between model size and performance when compressing BERT? And two, given these trade-offs, can we make informed decisions on a model architecture that best works for our needs? To answer these questions, let's focus on our use case, Distilling BERT for question answering. The dataset we'll be using is Squad 2. It is comprised of 35 topics ranging from the chemical properties of oxygen to the history of the Yuan dynasty. Each topic has a set of questions the model needs to understand and answer. So think of this as your standardized reading comprehension tests where you're provided a paragraph and a set of questions, and you need to find the answers to these questions within the paragraph. Unlike Squad 1, Squad 2 introduces the concept of unanswerable questions, making it more challenging for models. The dataset itself is split 50-50 between answerable and unanswerable questions. For answerable questions to be marked as correct, the model has to find the exact string match in the passage for the answer, but for unanswerable questions, the model only has to classify that the problem is unanswerable. This is not great, as the model can randomly guess that all questions are unanswerable and get a 50% accuracy. We'll deal with this property of the data further down the line, but for now, let's look at how distillation works. So distillation is a compression technique where a large, cumbersome model, the teacher model, is compressed into a smaller model, the student model. So during distillation, the teacher model is already trained on the dataset, and the student model is being trained through the distillation process. Unlike most model training processes, the student model's loss function is a weighted loss over hard and soft target losses, where the hard target loss is just your classic loss function where the model is trained on the dataset, and the soft target loss is this added component that allows the student to learn properties that the teacher model has already learned. So by combining both types of loss functions, the student uses this information to generalize the same way as the teacher model and reach higher model performance than if it were to be trained from scratch. So overall, the goal of distillation is to get a trained student model that is smaller than the teacher and performs strongly on the dataset. We'll use distillation as our compression technique and run it multiple times with different student model architectures. Our teacher model is BERT, pre-trained and fine-tuned for Squad 2, and we perform an architecture search during our optimization process to define the student model for each distillation cycle. Due to how distillation works, we also expect the student model to have learned properties from the teacher model that it would not have been able to learn on its own. And a quick shout out to Hugging Face. Without their transformers package and prior research on DistillBERT, this project would not have been possible. So now that we've defined our distillation process at a high level, let's look at how we're going to define the student model. We define the student model's architecture through suggestions from SigOpt. And as much as we can, we seed the model with pre-trained weights from DistillBERT, trained on the Toronto book corpus and English Wikipedia. So now that we've defined our distillation process, let's look at what our baseline looks like. For the baseline, we use the student model architecture from the DistillBERT paper. The distillation process uses a low temperature value and equally weighted loss function across the hard and soft targets. And the SUD parameters used are also the defaults from the DistillBERT paper. As a result, our baseline has around 66 million trainable parameters and reaches a 67% accuracy on Squad 2. So by optimizing this distillation process, we're going to see if we can beat the baseline's accuracy and come up with a student architecture that's smaller than 66 million parameters. So let's take a look at our optimization process. As I said earlier, we're going to use SigOpt's HPO solution, and specifically multimetric Bayesian optimization to optimize the distillation process and perform our architecture search simultaneously. So with this hyperparameter optimization technique, we're able to optimize for two competing metrics at the same time. And at the end of the optimization process, it'll populate a Pareto frontier. So each point on the frontier is an optimal trade-off point where you cannot improve in one competing metric without sacrificing the other. More concretely, what that means for us is that we'll be concurrently optimizing for model performance versus model size, where we want to increase model performance and decrease model size of the student model. And on the graph, we see again the baseline values for each metric that we're trying to beat. As we already know, the Squad 2 dataset is split across answerable and unanswerable questions. This just means that if the model is trained poorly, it's easy for it to classify everything as unanswerable and randomly be correct 50% of the time. There are a couple ways to deal with this. We could create a composite metric that better measures total accuracy, or use metric thresholds. Because composite metrics are difficult to create, we chose to set a metric threshold at 50%. This informs the optimizer to focus its efforts on parameter spaces that result in model accuracy over 50%, and we successfully avoid configurations where the model is randomly guessing. So what are we tuning? We'll be tuning training parameters, including SGD, batch size, and weight initialization. We'll be training architecture parameters, including the number of transformer blocks, the number of attention head pruning, and dropouts for the network. And we'll be tuning distillation parameters for temperature and the weights for the soft and hard target loss components. So at the end of this optimization experiment, our Pareto frontier will be optimal sets of model architecture and hyperparameter configurations, where we cannot improve in size without sacrificing performance, and vice versa. This is just an overview of our optimization cycle. SigOpt provides distillation architecture and the other hyperparameter suggestions. We create the student model and run the distillation process given these parameters. The resulting trained student model reports back its validation performance and size. SigOpt then takes these performance metrics and suggests the next set of parameters. And we continue in this loop-like fashion until the end of the experiment. In order to conduct this experiment, we use Ray to orchestrate our EC2 cluster. Ray manages the cluster orchestration and uses SigOpt for the parallelized Bayesian optimization algorithm. And we run our tuning process in parallel across 20 EC2 instances. So this is what the integration between SigOpt and Ray looks like. The native Ray-tuned SigOpt integration currently doesn't include our advanced HPO solutions, but due to the modularity of Ray and the modularity of SigOpt, it was really easy to integrate our multimetric optimization with Ray-tuned's orchestration framework. And I've highlighted a couple of key integration points, specifically how to create a SigOpt experiment within the Ray-tuned framework, and how to get a set of suggestions from SigOpt during runtime. So to run the tuning, we use the first in, first out scheduler from Ray-tune and rely on SigOpt to schedule the hyperparameter suggestions themselves. So what were our results? This is our resulting Pareto frontier. The yellow dots are the optimal points, and the pink dot is our baseline. By using the frontier, we're able to understand the trade-offs between model performance and size during distillation. We're also able to identify architecture configurations for the student model that result in these trade-offs. Essentially, instead of relying on a single architecture performing well for question answering, we're able to leverage these trade-offs and choose from a set of architectures. These are just a few optimal points I wanted to highlight. On the far left, we have our smallest student model architecture that performs as well as the baseline. And on the far right, we have our best performing model that is slightly larger than the baseline. Here are the respective architectures for those optimal points. Some common features found between the optimal configurations include the student model preferring no dropout and an emphasis on soft target loss. And we see that the architecture is compressed by reducing the number of layers more often than pruning the attention heads. What we see here is that by leveraging multimetric Bayesian optimization to conduct an architecture and hyperparameter search during a compression process, we're able to identify sets of viable models for our specific problem. And we're able to choose a model architecture that best suits our needs. So let's take a quick look at the experiment dashboard. So this is our experiment analysis page. Here we see the Pareto frontier of the experiment. We see the metric threshold that's been set at 50%. We're able to see which correlations happen or exist between a metric and a parameter. We're also able to understand which parameters most significantly affect each metric. So for accuracy, we see number of layers and learning rate being the top two. And for number of parameters, it's number of layers and number of heads, which is expected. And then here with our parallel coordinates chart, we're able to really understand if there are and what ranges, sweet spots exist for all the parameter values, as well as what are the correlations that we can identify amongst all the metrics and all of the parameters, if it exists. So this is all great, but we really want to know, was the model able to answer questions? So let's take a look at our best performing model. Our best performing model is at around a 70% accuracy. As we see in this graph, depending on the category, the model performs better or worse, with topics such as the Yuan dynasty, Warsaw, and steam engine being more challenging than others. To understand really what's going on, we're going to categorize misclassifications into 4 different categories. Mostly right, the model is off by just a little by either including more context words or things like punctuation. Mostly wrong, the model has gotten the answer completely wrong. Label no answer, the model predicts an answer despite it being unanswerable. And label has answer, where the model predicts no answer when the question is answerable. Although some categories have different majority misclassifications, across the categories, most of the errors we saw are labeled no answer, which means that the model was answering questions that are unanswerable. This is interesting because going back to why we set the metric thresholds, we were really concerned about the model randomly predicting that everything is unanswerable. So at least it swung the other way. So let's take a closer look as to why the model might be doing this. So the section on Warsaw is pretty representative of a lot of the categories and passages that are present in the data set. So this section spans a long period of time with complicated and convoluted historical events. We see very similar nouns in each section take on a different role. So the main entity, the city of Warsaw, goes through many transitions, and many different terms are used to describe the same place. In addition to that, the questions are tricky and ask about relationships between these overloaded terms. So for example, in the passage above, one answerable question is whose army liberated Warsaw? Versus one unanswerable question is whose army liberated Duchy? Where the text says the Duchy of Warsaw, and the model guesses Napoleon for both. So these entities are related, but have nuances between them that the model isn't able to pick up. It's not able to differentiate between Warsaw and the Duchy of Warsaw, or really understand that these differences are due to a temporal transition that is described in the passage. And many missed questions similarly follow this pattern, and it's definitely something to look into for future work. So why does this all matter? What we saw through this use case project is that by using scalable and intelligent hyperparameter optimization, we're able to easily understand trade-offs made during compression. And by understanding these trade-offs, we're able to choose a model architecture that best suits our needs from a vast set of optimal and viable architectures and hyperparameters. For more on this project, please read the full work on NVIDIA's dev blog, watch our previous webinars, recreate the experiment with the Git repo, and use the model checkpoints, and explore the experiment dashboard. And for a limited time, you can sign up to use SigOpt for free. So if you're interested, please join our free beta at the link written below. Thank you. And I'm going to open it up for questions now.